Brian, you sharing on Slack on Zoom?
Yeah, I'm sharing. I just unmuted, so I guess that'll be the microphone.
Okay, we're good to go.
Okay.
Everyone on Zoom, hi Zoom. Alrighty. So we're going to start our next part of our session. I'm super happy to reintroduce. Were you here the first time?
No, I wasn't.
Okay.
Yeah.
Introducing Brian Healy, my postdoc. He co-leads the ZTF Data Science group these days. He is in charge of the large-scale classification of ZTF sources using machine learning, does the features, does machine learning, does a ton of stuff. So we'll be talking about that, and then that's also the basis for the notebook today. Otherwise, super happy to have you.
All right. Yeah, thanks for having me. So yeah, my name is Brian Healy. I'm a postdoc here at U of M, and I'll be talking about the ZTF source classification project. Let's get right into it, starting with the outline. So I'll start up just by describing the project, including the classification taxonomies that we use, the workflow that takes us from the ZTF light curves to the classifications we're interested in, including feature generation, machine learning algorithms, compute resources, and also the human classification review that we've used to build up the training set called active learning. Then I'll conclude with the current SCoPe status, and then I'll introduce the Jupyter notebook that you'll be working on later on. So by this point, you're probably pretty familiar with ZTF. Just as a reminder, it's a Northern Sky survey at the Palomar Observatory, and it has a wide field of view, a fast survey rate, and it observes sources in the G, R, and I bands, and it achieves a median single visit depth of 20.6 magnitudes at 5 sigma in the R band, so nice and reasonably faint. And it provides full sky coverage of its observable sky every 2 days during the survey. And it's very large scale data. So in the most recent data release, DR18, that covers between March 2018 and May 2023. That includes 49.6 million single exposure images and 4.7 billion light curves. So this is definitely going to require automated analysis optimized for speed and scale to achieve our classification goals at this level of data quantity. So I like to start out always talking about SCoPe, showing some example ZTF data, just a time series and a few different bands to get everyone on the same page about what we're trying to do. So this is a light curve for a W Ursae majoris type contact binary system. So it's eclipsing sources, they're actually in contact with each other. And yet, I don't know, from here, just looking at the time series, I really just I don't see the astrophysical nature of it. I just see, the gaps in the light curve, depending on the time of year that it's being observed. I see different sampling rates, depending on, sometimes there's faster cadences. You can see that kind of the straight line there in the R bands that actually is just much more tightly spaced data points. It becomes much more apparent, much more apparent what the source is when you face fold it on the right period. So here you can now see the eclipses that the system is showing when you look at it, and it's folded on a period of about 0.35 days. But there are many other kinds of sources hidden within these light curves. So here's an example of a flaring source. There are fewer points here. It's mostly R band, but you can see that there are these large deviations from the typical magnitude in this case. So just another kind of star here, but it's not just stars. You can also have an AGN. So here's an example of that, active galactic nucleus in the 3 different bands, and just how that looks in the time series. And it can often be very difficult to, certainly by eye, even for the algorithms, to distinguish between astrophysical sources and artifacts. So for example, on the left here, I've got another kind of eclipsing system, a beta Lyrae type system, and that time series. And then on the right, I've just got an artifact created by the blend of 2 nearby sources. So there do seem to be some similarities I see between those light curves, but they're from totally different sources. So just motivating showing the difficulty of how this how source classification can go. So so just to motivate that a little bit more. So of course, source classification of all these billions of sources will benefit variable star studies. So it'll enable ensemble studies if you provide millions or more of a certain kind of variable star, then that's very interesting just on its own. Now, very near and dear to our group here at U of M is kilonova follow-up. So this is another benefit of source classification. The idea is that when we see these transient candidates presented by ZTF, they may happen very close to an existing variable source, and that's very interesting and relevant to know about. So if we can classify those sources, then we can exclude certain candidates or just have as much information as we possibly can about certain transient candidates based on the variable sources near to them. So especially if they exhibit any kind of past variability that we can pick out from the existing source classifications, then we know that that's not the transient we're looking for. And so then finally, source classification is useful for anomaly detection. So we can discover new kinds of sources by searching for anomalous outliers in the classification scheme that we've set up. So I'll get into that scheme a little bit more going forward. So this leads me to the ZTF source classification project, or SCoPe as we call it. So it combines machine learning algorithms with human feedback to reliably classify variable ZTF sources. And just a little bit of relevant terminology, some of it may be pretty familiar, but just to cover it, it's supervised learning. So we use a subset of sources with existing classifications to train our ML algorithm. We input into these algorithms features that are you could either just use the light curve points themselves, or as I'll get to, extracted information from the light curves. And then the output we get is the labels or the classes. I'll use those two terms interchangeably, and those are the names of the source classifications for each source that we're studying. And so this the SCoPe project is hosted on a GitHub repository that is shown here and linked here, and it is open source. It's mostly Python based. We try to run it as professionally as possible, so we have a continuous integration, continuous development pipeline. We test things to make sure that incoming changes to the code don't break what we already have. We have code review, and we also have regularly updated documentation. All right, so I said I was going to get into a little bit more about the classification scheme that we use. So we have a few options here to consider. They are a multi-class, a multi-label classifier, or a binary classifier. So there's drawbacks and strengths to each one. So starting out with a multi-class classifier. So this, among many different classes, picks one correct label for a source. But this is very restrictive because we're classifying a whole bunch of different kinds of sources. The data are very inhomogeneous. So just to say that there's one correct label for a source it's not broad enough for what we're interested in. So one way to address this, or one component of the multi-class classifier, is a hierarchical scheme. So the idea is that you can know the parent class even if you're unsure about the child. So that's useful. But so then the next option we can consider is a multi-label classifier. So this provides simultaneous predictions for all the classes that we want to consider. But here the challenge is that the meaning of the classifications, and especially their probabilities, that's going to change every time we update the hierarchy. Every time we add more labels into that taxonomy, where the previous results we have are going to be potentially different because we're considering all these classes simultaneously. So what we've decided to end up doing for SCoPe is to use independent binary classifiers for every label that we're considering. So first of all, this does mean that we're going to have a lot more computational complexity or just expense involved in this, because instead of just one classifier, we now have potentially dozens or more. But the strength of this is that it's flexible to new classes. So as we add more labels that we're interested in, it's not going to change the performance or the results of any of the classifiers that we have already implemented. And it's also going to allow us to have multiple labels per class per source. And so that's very useful. Say, what if you have an eclipsing system where there's also a flaring star? Then you want to make sure that you have both of those realities represented in your classifications. So we organize these classifications in taxonomies. And so we need at least one of these that contains the hierarchy that we're going to use. So even though we have binary classifiers, it still is useful to have a hierarchy that shows how these labels are related to each other. And so here, overlapping classes pose a challenge. So imagine a young stellar object, a YSO. That can be many things. It can be flaring, it can be eclipsing, it can be eruptive. So if we're establishing a hierarchy, how do we minimize the complexity of this? Because otherwise we could have there are also sources that are flaring or eclipsing or eruptive that are not young stellar objects. So you can see that there could be pretty quickly some challenging complexity if we use just one taxonomy. So what we instead do is we split these labels into phenomenological and ontological categories into two different hierarchies to better avoid these overlaps between like the example here and many others. So I'll start out just by showing you a diagram of the phenomenological taxonomy to just show you how things are related. So again, remember that each of these labels here has an independent binary classifier that's training just on that label. But nonetheless, we do set up this hierarchy just so that if say in the training set, a source has been labeled as eclipsing, then we make sure that it also has been labeled as periodic and variable, just so that the parent classes are also represented in their binary classifiers. So but yeah, this is the phenomenological taxonomy. It only has to do with the shape and nature of the light curves themselves. It doesn't consider any external information. So then we have the ontological taxonomy. So this has to do with the intrinsic nature of sources we're classifying. So you'll see a lot of familiar astronomical terms here, astronomical classes. And again, we relate them such that we make sure that if something downstream is classified in the training set, then we also make sure that the other binary classifiers upstream will consider that source as well as a positive example. So those are the taxonomies. So now I'm going to show a diagram of the SCoPe workflow that kind of relates all the different tasks that we have to do to make this project work. So I'll go through them left to right. So we start out with our light curves and external catalog data in a database on the left. And so we query that database to then get that information. This is the Kowalski database. I'll describe it a little more in a bit. And then we generate features from the light curves and external catalog data. And I'll get into that more in a few slides. So then there's before I even started working on this project, there's initial labeling by human labelers to go from these sources and their features to some training set of data to use for subsequent training. That led to the first set of classifications. And then those were put through a neural network ML algorithm to then give us a bunch of trained models, again, one per label that we are considering. And so then with some more computation, more queries and more computation, pulling more features from that part of the process, you can then run the trained models on unclassified sources and get inference results. And then we used a tool called Fritz to then post those on a place where humans could then review those classifications, or at least a subset of them, decide whether the algorithm was correct for a given number of sources. And then through that expert review in the process of active learning, then have more classifications that we could use to build a bigger and better training set. And then so continue cycling in that process on the right until we're satisfied with the performance of the classifiers. And then the idea is that the final set of classifications will be uploaded back to the database as a product that can be used in however many different ways people want to use it. So that's the workflow. And now I'm going to get into some of these components of it a little bit more. So like I said, the database that we use for the light curves from ZTF and the external catalogs is called Kowalski. I think it's been talked about in the past few days. So this is a MongoDB archive and alert broker that we use, and it contains many things, among them exposures, light curves, external catalog data like Gaia, Allwise, and Panstars, and of course the transient alerts that we've been hearing about, and then from this project, the source features and classifications. So getting a little bit more into the feature generation process. So like I said before, you can just use the time series data as the input to the ML algorithms, but the challenges there are especially in that the sampling rate, the inconsistencies among different sources in the light curves for reasons having nothing to do with astrophysics make it challenging to do this. So you can imagine that a classifier might pick up on maybe where the gaps are, or whether a source has a sampling, that tighter sampling rate of data for any part of its light curve. All these things that we really don't want it to be learning, it could learn by just feeding it the time series. So what we instead do is we generate a bunch of numbers from the light curve to then input to our algorithms. So those just include some summary statistics that I'll describe a little more, as well as some image data that we actually feed in. So I'll talk about how we generate that, because it's not the images from ZTF. It's actually a 2D histogram. So yeah, we don't want to use the light curves themselves, uneven sampling, high noise levels. And so these standardized statistics decouple the classification from light curve inconsistencies. And so we generate 60 core statistics that are split into phenomenological and ontological categories to go along with the phenomenological and ontological labels that we're trying to get at. So starting with the phenomenological features. So these are the features that any phenomenological classifier, like the variable, the periodic, the irregular, is trained on. So we get them only from ZTF light curve data. They include basic stats like the mean, median, magnitude, variance, interpercentile ratios, skew, kurtosis, and other statistics that are named after people. They also include Fourier statistics. So if you assume for a minute that we can get a period for these light curves, then we can return the parameters describing a Fourier series that's been fit to the light curve. So that includes the power, the amplitudes, the phases, etc. So those are also included in the phenomenological features. And so these are, like I said, these are the only features for training phenomenological classifiers. They're also a subset of the features for the ontological or intrinsic classifiers. But to those, we also add 25 more features. So these are coming from sources that are external to ZTF and the light curves. So they're only included in training for ontological labels. They're obtained from non-light curve data and catalogs, as in non-ZTF light curve data. So these include the Gaia EDR3 parallax, along with the BP and RP magnitudes and errors. They also include all-wise and pan-stars magnitudes and errors, just to get more information about the color of the source in different bands. And it also includes a little bit of information about ZTF alert info, specifically the number of times that there was a ZTF alert for the source, as well as the significance of that alert. And it also includes the significance of the computed period that we use. So, because not every source is going to be periodic, and so the significance is important there to help inform that part of it. So I said just assume that we can find the period. Now I'm going to get into a little bit more how we do that. So one straightforward way to find periods from time series data is a Loam-Scargill periodogram, but that takes about roughly 1 second per light curve to run on my laptop CPU. So when you have billions of light curves, every second really counts, and that would be a prohibitive amount of time to run period finding that way. So what we instead do is we take advantage of other hardware that's available. So we use GPU accelerated period finding algorithms to reduce the runtime per light curve to about 0.1 seconds per light curve. We get about an order of magnitude speed increase there. So we take advantage of the fact that GPUs are very good at parallel processing. They might have thousands of cores compared to a handful of cores for CPUs. And so that's really good if, say, you have a grid of periods you want to determine for something like a Loam-Scargill algorithm, like the significance of that specific period. And you can run that for a lot more periods at once on something like a GPU compared to a CPU. And so we don't only run on one GPU, we actually run in parallel on something like 20 GPUs at once on a high performance compute cluster called SDSC Expanse to then further accelerate the process. So you can divide everything by a factor of 20 there for the runtime. So just a little bit more about the GPU accelerated period algorithms that we use. So the first is a Loam-Scargill periodogram. So this is a least squares approximation to a Fourier transform of the light curve. We also run what's called a conditional entropy period finding algorithm. And so here we minimize the conditional Shannon entropy of the light curve's points when you fold it on a bunch of trial periods. And so you have to give it that input set of periods. And again, then you can parallelize this on the GPU so that you're trying a bunch of periods at once. And then we also run an analysis of variance. And so this compares the means and variances of light curve points that are folded on these different trial periods. And so these are the three algorithms we try. We also then run a fourth algorithm without much more computational cost. And that's actually a nested approach where we take the top 50 Loam-Scargill periods and the top 50 conditional entropy periods, then throw those 100 into a smaller scale analysis of variance. And then we get a period from that. And so this then can improve the period finding over just running any one of these algorithms individually. So I mentioned before that we also include some kind of two-dimensional image data in our features. And so these are magnitude time histograms, or dmdt. And so these map changes in magnitude and time to 26 bins. And so if you imagine each light curve, each pair of points within a light curve, you can compute a change in magnitude and a change in time, and then bin that up, plot it in a two-dimensional histogram, and it looks something like this. So this effectively creates a standardized kind of image as an additional feature that we can use in our classification. And just to show you how different it can appear for one kind of source versus another, I've got, again, the contact eclipsing binary, the W Ursae Majoris type star, has that looking, the dmdt kind of looks like that, where dm in magnitudes is on the the y-axis, and dt in days is on the x-axis. And then I've got a flaring source over here on the right. So I'd say the main thing that pops out to me is that those those upper and lower corners on the right are populated more because you've got these large departures from the median magnitude. So this can improve the algorithm's ability to classify. So speaking of which, let's talk a little bit more about the algorithms. So the first algorithm that we implemented in SCoPe is a neural network. And so just just to introduce it a little bit, so you've got these connected layers of what we call neurons that map the input layer to the output layer. And the input layer contains the features that we generated, and then the output in our case is going to be classification probabilities for the specific label we're interested in. And then these hidden layers in between in the neural network transform the features to achieve an optimal output. And so let's just zoom in a little bit. We've got this a bit more abstract, but within a single neuron, what's happening is that the input values are all weighted by a set of weights, the W's here, and then they're summed up, and there is a bias term, the B, that's added to it. And so then you get a number from that when you just use this formula over here on the right. And then you finish it off with some kind of nonlinear activation function. So you send that result through, say, a sigmoid or some other kind of nonlinear function that then is the output of that neuron, and that gets passed on to the next layer. And so that nonlinearity is key, because that's what allows deep neural networks with hidden layers to learn the complex relationships between input and output. So taking it one step further, since we do have two-dimensional kind of image data in our features, part of our network is convolutional. And so what we do here is, rather than just handling a set of numbers, like single one-dimensional numbers, we actually we take this two-dimensional histogram, we run it through convolutional layers and pooling layers to then reduce these images to its own set of 1D features that the algorithm determines. And then we combine this with the other generated features that I mentioned before to then feed it through a fully connected neural network and get the output, the classification probability that we're interested in. So here's a diagram of the SCoPe neural network architecture. And so it has these two branches, again, because we have a convolutional branch with the dmdt magnitude time histograms, and then the rest of the features go into the other branch. And so most of the features begin where it lists features there, but then the histograms are put through these convolutional and pooling layers before they meet up with the features at the bottom of this diagram here. The dropout layers that you can see here, like dropout and dropout 2 and et cetera, they help, they introduce a process called regularization to the network that helps to avoid overfitting by randomly kind of severing the connection between some fraction of neurons between layers. And so that helps to avoid overfitting, where we're learning how to represent the training set well, but not really how to generalize to other sources. And so then the classifier output, like I said, is the probability of the given label of this specific classifier for each source. So again, there are dozens of these, all training on a different label. So the training set currently has about 80,000 sources in it, and that translates to about 170,000 light curves. And the reason that it's not the same is because ZTF observes in multiple bands. We treat each band separately. We also, even if it's in the same band, if ZTF has observed a source in more than one field, we'll also treat it as two separate light curves. And this takes into account, or this is because of systematic differences between filters and fields that can arise. So when we train, we use a loss function to evaluate each epoch of the algorithm's run, and we try to minimize that loss function. And in doing so, the process of doing that is by improving the neural network weights and biases that I mentioned before by using backpropagation. So that's basically, if you run one epoch of the neural network, you compute the loss function, you also compute the gradient of the loss function and how it changes with respect to each path that the input features take through the neural network to get to the output. And then by having that set of partial derivatives, you know kind of which way to tweak the weights and biases of each neuron to get a smaller loss function. And that's how the neural network is actually improved. And so then there's also the question of hyperparameters for the neural network. So I think you've seen these before a day or two ago. We use weights and biases sweeps to tune the hyperparameters here. And it's a nice way, nice visual way to see the optimal combination of hyperparameters. All right, so I've focused mostly on the neural network, but we actually incorporated a second algorithm into SCoPe, and that's called XGBoost. And so this is a very different kind of algorithm. It combines a bunch of individual decision trees. So basically, if you, in a simplified way, if you imagine that if we just had one feature and you had you had one classification you were interested in, then if you had a very simple decision tree, you would just make a split where if the feature is greater than this value, it'll be a positive example. If it's less than that, then it'll be a negative example. But add more features and more layers to the tree, and then run them sequentially one after the other, then you basically get XGBoost. And so this is a algorithm that's powerful because it's very good at minimizing underfitting at the risk of overfitting. One other very good thing about it, unlike the neural network, which involves these hidden layers where we don't really know what's going on with the input features, we actually get feature importance information based on this algorithm. So because it's just making splits, very clear to follow splits in all the different features, we actually can then figure out which features were the most important for that specific classifier to determine whether a source should have a given label or not. And so we found that it achieves comparable performance versus DNN, the neural network algorithm, but it definitely runs faster as well. And I think you'll find that in the notebook. The notebook asks you to train a whole bunch of XGBoost classifiers, and then at the end run at least one neural network classifier. But there's definitely a speed improvement with XGBoost. So when we evaluate how our model is doing, we can use several different metrics. The ones that I tend to prefer are the precision and recall scores. And so these quantify the model performance at the end of the training epochs. So the precision can be thought of as the purity. So basically, if the model is labeling something as a positive example, then how often is it actually a positive example, or how many things that is labeling as positive are actually positive. The recall is also important. It can basically be thought of as the completeness of the classifier. So how many times is it falsely labeling something as a negative example when it should have labeled it as a positive? So these metrics are both important, both the purity and the completeness here, to make sure that we have a reliable model. So there's also, you could just consider the accuracy of the model. That's the number of correct predictions over the number of total predictions. But this can be very misleading for imbalanced classes. So for example, if we have in our 80,000 source training set, if we have 100 examples of a given rare kind of object, then if the classifier just labels everything in the whole training set as negative, then the accuracy is going to be very high, but it's not going to be giving us any useful information for that classification. So I tend to stay away from the accuracy because we do have plenty of cases where we have imbalanced data. And so then we obtain a trained model for each class. And so I'll show you now on this next slide the current precision and recall performance of all the different binary classifiers that we're training for both DNN and XGBoost. DNN's on the top, XGBoost is on the bottom. The precision is in blue on this bar plot, and the recall is in red. And so you can see we've got these different abbreviations for the labels, and there's a guide that you'll be able to find for what these actually all mean. But basically, so we see several cases where the precision and recall are both high. They're both 90% higher than that. But then there are some cases where, say, the blue bar is a lot higher than the red one. So these are cases where the purity is very high. If the model is classifying with high probability, then it's believable, but it is missing out on some of the positive examples that it should be getting. So generally, our training results tend to either be good for both precision and recall, or a little more leaning towards precision than recall. And then I also have to mention that there's some labels here where you don't see a bar at all. And what's happening here is actually that specific classifier has it's basically labeling everything as negative, like I said, it could do in the cases where there's very few training examples or inconsistently applied labels. So the one I think is most easy to explain here is the wrong period classifier. So that is the WP here and here. And so to have that one really be, to have the training data really be reliable for that specific classifier, we'd need the labelers to go through all those 80,000 sources, evaluate the period that was associated with each one and say whether it was right or not. But just based on the human time that was spent here, the human resources and what they were expert in, this may not have necessarily been done across the entire 80,000 source sample. And so even though there might be some cases where there's a wrong period classification, it wasn't really consistently applied enough to train the classifier well. So that's okay, because we have plenty of well-performing binary classifiers, and definitely in the course of training, I was taking a pretty optimistic approach to what labels might have enough positive examples to be considered to be useful for training a classifier. So there are some of those examples in the results here, but it's not something that really is indicating a kind of a major issue, just that, just kind of showing the limitations of what our training set has in it. All right, so after all this training, our goal is to run inference on unclassified sources. And so for this, we query the generated features that I went into the process earlier of describing, and then we run the trained models on those. And we obtain classifications and their probabilities from each binary classifier. And then again, the intermediate process here was to build a larger training set using the human evaluation of some of these ML classification results. And so this was called active learning. And so again, remember that there are multiple light curves per source and multiple classification probabilities per source, because each light curve gets its own classification probability. And so what I did was I combined those using the mean of the probabilities. So then now we're down to one set of classifications per source. And so then I selected the top n probabilities for each class, some reasonable number for people to actually look at. And then for these sources, I also included some other moderate confidence classifications, because to really improve the classifier, you don't just want to look at how it's performing at its peak. You also want to see the ones where it's kind of iffy, and then maybe nudge it in the right direction by having humans look at some more of those labels, decide that some of them are right, and then incorporate those into the training set. And so one other important part of this is that you need a user interface to rapidly see this information and make decisions on the classifications, because again, the more we can do here, the better, but we're using human time here. So we really need to consider how we can do this in a reasonably fast way. And so enter SkyPortal and Fritz, which I think has also been discussed at some point this week. It's SkyPortal has its own GitHub repository, and Fritz is a hosted instance of the open source SkyPortal data platform. And so among Fritz's many things, among them a broker for ZTF alerts and an archive for persistent sources. It has many tools for follow-up, ML applications, and active learning, like we used for SCoPe. And it very much supports collaborative efforts, and it provides both API and front-end access to all of these features. So I'm going to show you a few screenshots here of the front end, just to show you what the labelers were doing when they were performing the active learning process. So here's what Fritz looks like. This is a group on Fritz with a bunch of sources. They're all listed in the different rows. And what you can see is there's some basic information like the right ascension and the declination. And then what we're really interested in for SCoPe is the classifications. So these are machine learning classifications that I believe, the neural network determined for these sources. And so what we then wanted the experts to do, the human experts, is to go in and basically decide classification by classification, source by source, whether they agreed with these or not. So if you drop down the arrow on the left for a single source, then you can see a little bit more information right on that same page about the source. So the time series information, the phase folded light curve based on the period that was provided, and some cross match information, in this case with the Gaia survey. And so then if that wasn't enough information to decide on these classifications, you could also click into the source and click on the source ID there. And then we also provide an interactive Loam-Scargill periodogram, just to, if the phase folding wasn't right initially, then you can actually see the full periodogram here that's computed on Fritz, and then you can click on the different peaks of the periodogram to see the phase folded results. So I think it's really neat. You can also quickly, it's oftentimes the case that the period is determined correctly only up to an integer multiple. So then you could quickly consider the half multiple or the 2x multiple of the period that's given and see how the light curve looks based on that. So just, again, trying to help these human labelers decide whether the light curve they're looking at is receiving the correct ML classifications. So then once they were decided on that, they would then go back to the group source page and then mouse over each classification that you see here, and then they'd get this voting interface. And so you can see they could, depending on whether they agreed or not, they could vote for every specific classification, thumbs up or thumbs down. And to make things even quicker, if they agreed with all the classifications or disagreed with all of them, then they could give a blanket thumbs up or thumbs down to everything. And so then it would record the vote, and then we would consider these votes when going through Fritz later on and looking at these sources, and then anything with thumbs up would be added to our training set. And so that's good for the existing ML classifications, but we also needed an interface to add additional classifications, because they're, especially if the recall is, kind of trailing behind the precision for the algorithm, then it might have missed something. And so for that, we have this slider interface here. And so this is just a drop down below the source. And you can see then the hierarchical relationship between the labels here. And so if there was something that was missing, then you could drag that slider to the given probability you wanted to give it, and then submit those classifications, and they would be added along with an automatic upvote to the existing ML classifications. And so, and we also had code here that would allow you to basically make sure that if you were the labeler and you were only focusing on, say, like, well, this one's definitely sinusoidal, then it would also make sure that if you drag this one to here, then it would also drag the periodic slider to the same spot, because then we want to make sure that again, even though we're training binary classifiers, we don't want to be we want to make sure that upstream we're also including any labels if a human was confident in the downstream label. And so then finally, once votes were cast or classifications were added, then this labeled box would automatically be checked in Fritz. And so then this would allow labelers to pick up where they left off. So they could basically filter the sources in a list by whether they had labeled it or not. And so again, just trying to optimize the time that the humans were spending to help us out with this. And so one other thing to note is that we decided after a little discussion to hide the votes by default to avoid biasing reviewers who were not the first to look at a source. Just a little detail there that I think was a useful thing to add. Okay, so that's the active learning process. So I'm just going to talk briefly about the current status of SCoPe. And so we've been generating features on ZTF based on ZTF DR16 for 20 ZTF fields that for the length of the project have kind of served as the benchmark 20 fields. They represent different parts of the sky, different stellar densities from the galactic plane all the way up away from that. And so we've been using SDSC Expanse GPUs to generate those features. And so that's complete now. So we've obtained classifications from both the neural network and XGBoost algorithms, and you've seen the precision and recall performance of both these algorithms based on the training performance on these DR16 features. And so then every 2 hours or so, going back to the connection with Kilonova follow-up, these trained models are actually running on any ZTF sources within half an arc second of transient candidates to assist with follow-up decisions. So they'll identify any ZTF sources, then generate features for the available light curves, and then run the classifications. And then those SCoPe classifications will actually be posted alongside any classifications for the transient itself, just to, again, help the scanners have as much information as they can about the transient itself and anything that's nearby to it. And so we've got a paper in prep to report the methods that we've used for SCoPe and the resulting classifications. And a major deliverable of this publication will be a catalog of variable source classifications containing hopefully at least tens of millions of sources to then be made public for any other work going forward. And so just to revisit this workflow diagram based on kind of where we are in the project. So this the feature generation is definitely the most computationally expensive part of this process, especially the period finding. And so that's kind of the bottleneck to getting to the point where you can classify all of ZTF, just because 4+ billion sources is a lot. So we're working on ways to hopefully optimize the feature generation algorithm and just continue to keep access to the resources that we use to speed things up. And with, again, the end goal being to get these classifications, the final set of classifications for all of ZTF on a database. It's just a summary of the talk in general. So time domain survey astronomy requires new automated analyses to deal with all the data that we have to work with. And ZTF SCoPe is one of these. And so the goal is to produce a reliable catalog of classifications for all ZTF sources. And so just as a reminder, we use binary classification to do this. And we use labels in 2 different taxonomies, phenomenological and ontological. And so we train neural network and XGBoost algorithms and then grow our training set using active learning. And we accelerate these processes using GPUs and many GPUs on an HPC cluster. And so just looking ahead, LSST Rubin is going to be, is coming up in a few years, and that's going to be operating on something like a 10 times larger scale than ZTF currently is. So all the things that are challenging us now that are making us, streamline our algorithms and get the resources that we need to really run this at scale are going to be at least something like 10 times more demanding in a few years. So just interesting things to think about and consider. So I've got a few more slides based on the notebook, but I think it's a good time to, I don't know, I could pause for questions now, just on this part of it, and then go into the notebook introduction after that. So thank you.
When you're doing train test split, are you doing that on object value or the light curve?
When we do the train test split, we're doing that on the light curves.
Is that not with the feature?
Yeah, so let's see. Let me just make sure I'm answering you right. So yeah, we download sources and we have the light curves, and yeah, let's see. I think no, actually, so you're right. It would be important to make sure that we're not like putting. So yeah, I think we do train test split on the light curve. So there is a potential that then a source could be like the G bands could be in the training set, and the R bands could be in the in like the test or validation set. So yeah, but yeah, I guess that's just kind of a consequence of how we, again, considering that there are different systematics between fields and colors, it's important to do it in this way that, kind of goes light curve by light curve because of the differences that can be manifest between them. There's a hand raised online.
Hi. Yeah, thank you for the wonderful talk. I do have a question about the features. You generate features and then you use all those features to train your model, or you do some feature selection, like some best features to train the model?
Yeah, so we are using a subset of the features that we generate, but right now we really we use a subset, but it's just kind of the subset that we have been using, and again, some for phenomenological and then a larger set for ontological classifiers. And so yeah, we're not at this point, we're not it's something that we're interested in going forward, but we're not right now using the feature importance from the XGBoost training to then identify a smaller subset of features that we can use. But that's something that will be, I think, of great interest going forward, because yeah, we definitely, especially amid all these scaling issues, we don't want to be reducing the number of features that we need to do this classification, not increasing them. So that's definitely a direction to head going forward.
Okay, so then how you select those subset of features?
Yeah, so I mean, basically the right now the only selection we're doing is the just kind of the sticking with there's a paper published on SCoPe in 2021, and just kind of sticking with those features that that we were using for that paper, but and so then the other features that we generated just kind of to be included in the database as ones that might be of interest in the future. But so yeah, I guess going forward, I would envision that maybe we use especially the XGBoost feature importance results to then pick, say, a top subset of all the features you're using and just try training on those and see if the results are comparable.
Yes, because if you're using a subset of features and you're using all the machine learnings and all the tools, then it would be better to use a feature selection algorithm like the XGBoost, or maybe there is a lasso algorithm as well to do the feature selection. So it would be great too, because I think if we have a subset of features, like that would be the best features to tell based on the machine learning algorithm. So I think the results would be the training of the model would be, I think, much better.
Yeah, I agree. And yeah, XGBoost is definitely a more recent incorporation into the SCoPe workflow. So it still kind of in the process of checking out those results and seeing what they say. But yeah, I think definitely of interest going forward.
Yes. Oh, okay. Thank you very much. Yeah.
Any other questions from the room or Zoom? All right, then I think just have a few more slides about the notebook that you'll be working on. So I'll get into those. Okay, so first, just about what's available to you on Google Drive. So because you don't have access to Fritz, usually we download the training set from Fritz, but instead we've got these files on Google Drive for you. So the link is here, and I imagine I'll be able to put this presentation on, upload it. So you'll be able to click on that link, and you should be able to get access to everything just by clicking the link. And so first thing, the main thing that you'll be working with is the full training set. So about 170,000 rows of data and 247 columns. And so this is, it's stored as a Parquet file. So if you're not familiar with that, then you can see the SCoPe documentation. There's actually a little discussion on why we're using Parquet versus like CSV or HDF5. And so the columns generally are organized such that you start out with the object ID, and then the right ascension and the declination associated with that light curve. Then you have the labels. So there's a column for each label containing a probability, and then a bunch of features that some of which go into the algorithms. And so there's a more detailed training set column guide on what it's called the SCoPe training set column guide Google sheet that's also on that in that Google Drive. So check that out if you want more information, and especially about like abbreviations and any column names you don't understand should be very helpful there. There's also, I don't think you'll need it. The way the notebook is designed right now, I don't think you'll need this 10% downsample training set, which only has about 17,000 rows. I think the things the notebook asks you to do now will run in a reasonable amount of time on the full training set, and I think that's that's the better way to go. Just so it'll basically mean that you might only be able to train one neural network classifier, but that'll still be useful to compare to XGBoost. And if you have more time, you're welcome to train more. But just so you know, you can generate that 10% downsample training set just by running this code. If you read in the full training set, and then it's a data frame, a pandas data frame, you can sample it by a fraction of 0.1. You can use that random state if you want to, for any reason, get the exact same set of rows as is in this one on Google Drive. And so then there's also there's the SCoPe model performance. So the stuff that I plotted on those bar plots in the form of JSON files for both DNN and XGB. There are about 5 or so performance metrics for each classifier in these JSON files on Google Drive as well, if you're interested in that. So there's pretty extensive documentation about SCoPe installation and testing, and I'm happy to help out with any issues that come up. But you can follow the documentation that's linked here. You can, and you definitely want to start out by creating your own fork of the SCoPe repo on GitHub. And then once you follow the installation instructions, I suggest running this code here, scope.py test limited, and that'll just hopefully reveal any additional errors that might have happened during installation. And it's limited because the full suite of tests requires Kowalski database accounts and access. So this limited test should still be enough to test the basic imports and things like that. So you'll know that you have a good installation. One important detail I think it's worth like verbalizing is that we use this config.yaml file to specify a whole bunch of details about SCoPe, including training details. So the first thing, one thing you want to make sure you do is copy. We have this file called config.defaults.yaml in the repository. You want to make sure you copy that to a file named config.yaml and then edit the config.yaml file as you see fit, as you need to get the code to run. So specifically, I think the only thing you'll really need to modify in that file to get this notebook to work is in the training section of the config. It's just one entry, the data set field right up top here, training and then data set. And so this is the path starting from the SCoPe directory to the training set that you'll be using. And so that's the default right there, but you're going to be downloading a data set that it'll be in a different place. It'll have a different name by default. So you'll just want to make sure you change that, or it'll throw an error when you start running the notebook. So, but if you're interested in modifying, say, other parts of the training, then you can do that down below here. And it's a pretty long file with just kind of all the configuration you might imagine for the different parts of the project. Okay, so just a few other notes. So SCoPe has utilities to read the Parquet files like the training set you'll be using. So as well as manage data sets. So I think one that, if you do want to inspect the data set some more, then just import this read Parquet function from scope.utils, and it'll save you a few lines of PyArrow code that you don't need to worry about. And also, like I said in the talk, some of the labels in the training set might be inconsistently applied. Like, for example, the human labelers just might not have looked at all 80,000 sources for the wrong period classification. So when you're starting to see, some of that, these variations in model performance, that might be why. And so then just the name of the notebook, it's this day04_SCoPE. It should be on the ZTF Summer School repository now. And so unless there are any questions, then that's the last slide I have.